All right. Good afternoon. Um, this is just an announcement for JCC's main campus being closed. So anybody who is having face-to-face sessions at 2 o'clock, as opposed to online, synchronous or asynchronous, those classes were canceled. Okay, for number 35 on page 280. Okay, we're looking at once again polynomial division, whereupon we have x to the fifth plus 32 is divided by the binomial x plus 2 okay. Now we left off, okay, with the remainder and factor theorems, and we're going to look at those once again. Now for x to the fifth plus 32 divided by x plus 2. Now again, just kind of touching upon the setup in accordance with long division. Okay, so you have x plus 2 into x to the fifth plus 32. So we have with the dividends, you have x to the fifth, and regardless of whether you use long division or synthetic division, make sure that you have a representation of all the degrees going down from the highest order in the polynomial down to the constant. So we have a missing x to the fourth, as well as a missing cubic term. And also we have a missing x squared term. And we don't have any first order x term present. But we do have this polynomial to close out with 32. Okay, so, and looking at taking x plus 2 into this fifth order polynomial. Again, the divisor is our first order. So instead of doing the very long process of the long division, I can take what I have here and translate in terms of synthetic division. So I have x plus 2 is equal to 0. So we have the x is equal to negative 2. And I'm going to add a statement to this, okay, because I'm going to tie in the remainder theorem. So x equals negative 2. So we have x is equal to c is equal to negative 2. Now for what I have taking on the side of synthetic division, so for synthetic division, so representing x plus 2, I have negative 2. And lining up the coefficients of the dividends. So for x to the fifth, I have 1. And then I have 4 zeros. I'm going to have the number 32 at the end. Okay, and so just looking at taking what we have and initiating the synthetic division process, like doing the column by column adding. Okay, so we have first constant in the dividend is going to be also the first constant in the quotient. So 1 is going to be brought down, and then we have negative 2 times 1 is negative 2, and then adding 0 plus negative 2 is a negative 2. Then we have negative 2 times negative 2 is positive 4, and then we have 0 plus 4 is 4. Negative 2 times 4 is negative 8. 0 plus negative 8 is minus 8. Negative 2 times negative 8 is positive 16. 0 plus 16 is 16. And negative 2 times 16 is negative 32. And 32 plus negative 32. Okay, so that is going to go to 0. Okay. Right. So again, the last column total is going to be the remainder. Again, the remainder is equal to 0. Okay. And just want to mention, okay, again, just with the remainder theorem, So for the remainder theorem, okay, if the polynomial f of x is divided by x minus c, then the remainder is going to be f of c. Okay, now, so with the remainder theorem approach, we can have f of x equal to x to the fifth plus 32 Now we're still working with the same divisor, x plus 2, and with the remainder theorem, now the remainder again you have equal to f of c. And guess what? Referencing earlier. Okay, we had x equal to c is equal to negative 2. So I'm looking at f of negative 2. So again, so you have x is equal to c is equal to negative 2. So with the remainder theorem, this will be the value of this function whenever x is set to negative 2. So I'm going to have negative 2 to the fifth plus 32. And negative 2 to the fifth, okay, that is going to be a negative 32. And negative 32 plus 32, okay, that is equal to 0. So you have these two ways of getting to the remainder. And if you notice, okay, we have from the synthetic division and with the remainder theorem, okay, we end up with the same value. And this will be each and every time, okay, whenever the divisor, okay, is a first order x expression. All right. And we have similarly, okay, we have for number 36, okay, so we're going from fifth order dividend to one that is fourth degree. And in number 36, okay, so you have x to the fourth minus 81, okay, it's going to be divided by x plus 3. Now, in the case of the long division setup, okay, so I have x plus 3 going into x to the fourth minus 81. Okay, so you're going to have a bit of history to repeat, especially with x from x to the fifth plus 32. You have a gap of missing degree terms. So we're missing here, this time missing a cubic and a square and a first order term in x. But we still had the dividend to close out with a constant, and where the constant is going to be at negative 81. And just taking what we have in the case of the kind of setting up the backdrop for the synthetic division as well as the remainder theorem. So again, we have x plus 3 is equal to 0. And we have x equals negative 3. And just in remainder theorem terms, okay, so your f of c is going to be f of x. So c and x are going to be the same value, which we will have at negative 3 once again. And so we have crossing over to what we have in synthetic division. Okay, so again, representing x plus 3, we have negative 3. And then for the dividend, we have the coefficient from x to the fourth at 1. And again, we have 3 zeros in the array since we have back-to-back missing degree terms from the third order in x all the way down to the first order. Again, we have closed out with the constant minus 81. And so we have in the process. Okay, so we have, so 1 is at the front, and it will be brought down. Negative 3 times 1 is negative 3. So shifting over to the next column, we have 0 plus negative 3 is negative 3. And then we have negative 3 times negative 3 is going to be at 9. 0 plus 9 is 9. Negative 3 times 9 is going to be negative 27. 0 plus negative 27 is minus 27. Negative 3 times negative 27 is going to be at 81. And negative 81 plus 81. Okay, so that is going to be at 0. So we have history to repeat, again, where the remainder is equal to 0. And once again, with the remainder theorem approach, again, so we have f of x is equal to x to the fourth minus 81. And again, for the remainder, again, we have equal to f of c, and c represents the input x, okay, 0. Okay, so again, we'll have f of negative 3. And plugging in, okay, for f of x, okay, input x is changed up, okay, where we have x to the fourth becomes negative 3 to the fourth. We have minus 81, and negative 3 to the fourth, okay, that's going to be a positive 81. And if we take away 81, okay, so that is going to be at 0. Okay, and so again, we have, regardless of the approach, we still have the same value. All right. Now, okay, so if you have a linear divisor, okay, such as what we have with x plus 2 as well as x plus 3, the remainder theorem, okay, this can be a potentially quicker approach in terms of getting to the remainder. Okay, and we have it always will be, yeah. So in other words, like if like it's sort of like rock paper scissors in terms of which might be the better approach. The remainder theorem, the advantage to that is that you're not having to worry about the 0 placeholders, and so there's less work to do. But let's say that if your polynomial had like a bunch of negative signs, like negative 3 times x to the fifth minus 4 times x squared plus 2x, you know, minus 7, and one might have trepidations about working with negative values where the 0 that you plug in with all the negatives is up. You know, I might commit a misstep, like where I might end up subtracting when I should be adding, and vice versa. The synthetic division setup kind of alleviates that stress in terms of finding the pathway to the remainder. Okay, so it should, yeah, it's always going to be the same. Right. Now, in the case of just testing out, in fact, just looking at what we have with both approaches, and for number 41, okay, so we got 41 and 42. 42, I'm going to provide a little bit of brevity on this one, okay, because especially 42, that we can get a little bit long-winded. Okay, and now for 41, okay, we have f of x, okay, is equal to 2x to the fourth minus 5x cubed plus x squared minus 7. Okay, and I'm just going to go ahead and mention, okay, so in this problem, okay, this one is going to be divided by x minus 4. Okay, so this is going to be divided by x minus 4. So your divisor is going to be x minus 4. And again, the 0 of x minus 4. Okay, so that is going to be at 4. You can also say that with utilizing the remainder theorem. Okay, you have x is equal to c is equal to 4. Now, for what we have in the case of part A, okay, we're looking at evaluating f of 4. So if you notice, you're going to have your remainder whenever you have the polynomial to be divided by x minus 4. Again, you're going to have the remainder at f of 4. So just plugging in 4 for x. So you have 2 times 4 to the 4th. Minus 5 times 4 to the 3rd. And we have plus 4 to the 2nd. Minus 7. And here, 4 to the 4th. Okay, that would be 256. Yes, I have 4 times itself, and then times itself yet again. And then we have minus 5. Now 4 cubed, that's going to be 64. And we have 4 squared is 16. And we have followed by the subtraction of 7. So we have with 2 times 256. So this is going to be at 512. 5 times 64. Okay, so we had the subtraction of 320. And 16 minus 7. Okay, so that's going to leave us with 9. And for the difference here, we're going to have, see, this will be 521 minus 320. So for the remainder here, by the remainder theorem, okay, so you're going to have at 201. And if I perform, say, the log or synthetic division, I'm going to have the same remainder. Okay, so just going to mention, say we have, say with the log division setup, so you're going to have x minus 4 taken into, and again, so you have 2x to the 4th minus 5x cubed. We have plus x squared. And notice we are missing a first order x term. So plus 0x minus 7. And again, just taking what we have with synthetic division. So again, I had before, x is equal to c is equal to 4. And with synthetic division, let's carry this over. So we have 4 to represent x minus 4, since 4 is the 0 of the divisor. And so lining up the coefficients, so I have 2, negative 5, followed by 1. And again, because there is a void in the first order in x, so I'm going to have to place 0, and we have negative 7. Okay, so we have at the start, okay, so you have 2, it's going to be brought down, and we have 4 times 2 is 8. Then we have negative 5 plus 8 is 3. Then we have 4 times 3 is 12. And we have 1 plus 12 is 13. 4 times 13 is 52. Okay, now these numbers are getting larger. And we have 0 plus 52 is 52. And 4 times 52. Okay, so that is going to be at 208. And then we have negative 7 plus 208. Okay, so that's going to come out to 201. And again, we have the remainder equal to 201, and that's going to be the same as what we have for f of 4. Okay, so the remainder value will always be the same. Okay, and now, and what we have regarding number 42, and we have on this one, I mentioned brevity in 42, and actually I meant number 48. That was a bit long-winded. Now for 42, now we have g of x is equal to, and here we have a fifth order polynomial. So we have negative 3x to the fifth, and we have plus 2x to the fourth. And we have plus 6x squared and we have minus x plus 4. Now go ahead and mention, now this is going to be divided by x minus 2. Okay, so for the divisor, x minus 2, so just getting to the 0, both in the capacity of utilizing the synthetic division as well as the remainder theorem. Okay, so you have x is equal to c is equal to 2. And for part A, I'm looking on the remainder theorem side, where the remainder is going to be whenever this expression is divided by x minus 2. Remainder, once again, you have is going to be g of 2. So with g of x equal to this expression, we have g of 2 is equal to negative 3 times 2 to the fifth. We have plus 2 times 2 to the fourth, plus 6 times 2 squared, and we have minus 2 plus 4. Okay, and I'm just going to mention, now in terms of the approaches, now if you had to determine the remainder by the remainder theorem or synthetic division, now if if I had the divisor to be x plus 2, okay, well your value c would be at negative 2. So if I thought like negative 3 times negative 2 to the fifth, and then you have negative 2 to the fourth, negative. If I had like an excess of negative signs, I would likely go with synthetic division on this one. And that's just so as to avoid any potential sign mistakes. But in the case of what we have with g of 2, so I got negative 3. Now 2 to the fifth, that's going to be at 32. And for 2 times 2 to the fourth, now 2 to the fourth is going to be at 16. And we got 2 squared is 4. And we go ahead and squeeze in negative 2 plus 4, so that's going to be a plus 2. Okay, so you have negative 96. 16 multiplied by 2, that is going to be 32. 6 times 4 is 24. And again, we have 2 added at the end. And so for g of 2, for that remainder through the remainder theorem, okay, so you have negative 96 plus 32. That'll be negative 64. Negative 64 plus 24 is negative 40, and plus 2. So we have that g of 2 is equal to negative 38. And again, just through the synthetic division. Okay, we have x minus 2 into negative 3x to the 5th plus 2x to the 4th. Notice we do not have a cubic term, so we need a 0 placeholder. Then have plus 6x squared, and have negative x followed by the addition of 4. Alright, so again we had with the remainder theorem, again, g of c was g of 2, and in the case of synthetic division, okay, so you got, again, the 0 is going to be at 2, and for the coefficients of the dividend, so you have negative 3, 2, 0, 6, negative 1, and 4. Okay, so just taking what we have. Okay, so negative 3 is brought down. 2 times negative 3 is negative 6. 2 plus negative 6 is negative 4. And then we have 2 times negative 4 is negative 8. 0 plus negative 8 is minus 8. 2 times negative 8 is negative 16. 6 plus negative 16 is negative 10. And we have 2 times negative 10, so this will be negative 20. And we have negative 1 plus negative 20, so this will be minus 21. And 2 times negative 21, okay, so this will be a negative 42. And the last column total, we have 4 plus negative 42, so this will be at negative 38. Okay, so we have the remainder is at negative 38, and notice we had the same outcome for g of 2. Okay, so again, regardless of whether you use synthetic division or the remainder theorem, if you apply the proper algebra and have the right terms aligned, okay, you're going to come out to the same results. All right, now in the case of what we have with number 48, and there's going to be a tie-in with another theorem. And I mentioned this, I believe, at the end of yesterday's class. Okay, so we have in the case of the remainder theorem. Okay, so again, if f of x is divided by x minus c, then the remainder is f of c. And akin to this, and actually as a continuation, okay, we have the factor theorem. And this, once again, is going to be binary. Okay, so you have from the remainder theorem, okay, you got the remainder at f of c. At the remainder that we have for f of c, if that is equal to 0, if the remainder is 0, that means that the divisor is going to be a factor of the dividend. So in this case, you're going to have the x minus c is a factor of f of x. And if it turns out that the remainder, f of c, does not equal to 0, then we have that x minus c is not a factor of f of x. Okay, so we have, in the case of 48, okay, so we want to have tied in, okay, like the remainder and the factor theorems. And for the case in number 48, we have given a polynomial function, okay, which we have in terms of g of x. Okay, so with the remainder theorem, you have like, okay, it doesn't have to be f. You have like, if g of x is divided by x minus c, the remainder is g of c. And also, same thing here, if g of c is equal to 0, g of c does not equal to 0. So here we have in 48, we have g of x is equal to 2x to the fourth plus 13x cubed. And we have minus 10x squared. And we have minus 19x plus 14. Okay. And we have posed the question, okay, and that is c equal to negative 2 or 0? And another way of asking this is going to be, is x plus 2 a factor of g of x? Okay. And we can apply the remainder theorem on this one. Okay, so we got the remainder is equal to g of c and with c at negative 2. Okay, so negative 2 represents both c as well as x. And we have in the setup and calculating the remainder whenever the input is at negative 2, or the factor being x plus 2, we have 2 times, okay, negative 2 to the fourth and we have plus 13 times the cube of negative 2 minus 10 times, okay, the square of negative 2 and we have minus 19 times negative 2 followed by the addition of 14. So here we have negative 2 to the fourth is going to be at 16. And we have 13 times. Now negative 2 to the third, that's going to be at negative 8. Got minus 10. Now negative 2 squared is going to be at 4. Negative 19 times negative 2, that's going to be at 38. And again, we have plus 14. So you have 2 times 16 is 32. 13 times negative 8 is negative 104. You got minus 40. And 38 plus 14, so those numbers will add up to 52. And it's going to turn out that the weight of the negative terms will outweigh the weight of what we have with the positive terms. So we're going to have a negative result here. And so this outputs, those numbers will amount to negative 60. And so since the remainder is at negative 60, I'm just going to repeat. Okay, so the remainder is equal to g of c is equal to g of negative 2. Again, that was negative 60. And where the factor theorem comes in, okay, again, if it's 0, then it's a factor. If it's not equal to 0 in the remainder, then the divisor is not a factor. So here, we got negative 60. So that is not equal to 0. And so for what we have in consequence is that negative 2 is not a 0. And in effect, we also have that x plus 2 is not a factor. Now we have in the case of part B. Okay, so c equals negative 2 is not a 0 since the remainder is non-zero in value. But if I have that c is equal to negative 7, so this is also asking if x plus 7 is a factor of g of x. Okay, so testing out what we have with the input at negative 7. Okay, so the remainder we have g of negative 7. Okay, so applying the same treatment as I did with the input at negative 2, so we have 2 times negative 7 to the 4th plus 13 times negative 7 to the 3rd. We have minus 10 times the square of negative 7. We have minus 19 times negative 7 plus 14. Okay, now we're going to have some large numbers in the mix. Negative 7 to the 4th, that's going to be 2401. We got 13 times. Now the cube of negative 7 is going to be minus 343. And negative 7 squared is going to be 49. Now negative 19 times negative 7, that's going to be a positive 133. And we have plus 14. And if we follow through, taking the sum of these products and then the constants that follow. Now your result here, also, that's going to come out to 0. And so, since the remainder here is equal to 0, it's going to be by the factor theorem. Okay, so it's going to follow, okay, that the answer is yes, okay, negative 7 is a 0. Okay, so we also have chipping in, we have x plus 7 is going to be a factor of g of x. Okay, so negative 7 is a 0, okay, since the remainder is equal to 0, so that divisor is a factor. And this is going to tie in, okay, just some of the items we have been looking into, like going back to the FOIL method and working with polynomial, not just division but also multiplication. And we have also tied in when we were looking into factored and expanded forms of polynomial functions. And now for the topic that's going to sort of blend in a lot of the earlier elements from these recent sections. We'll have over here, we'll call this part determining polynomials or determining factors. Determining factors of polynomials from given zeros. Now we had given zeros like in the capacity of like forming a polynomial expression where we had like zeros or multiplicity and what the degree of the polynomial is going to be. It's not the same exercise. And this part is going to sort of tie in what we have dealt with in the synthetic division. Okay, and let's say that if we have so we have, for instance, okay, say if I'm looking at factoring, so we have f of x is equal to, we'll say we have 2x squared minus 6x plus 4 given that 2 is a 0. Okay, so you got given that 2 is going to be a 0. Okay, so what I'm going to do here, I'm just going to go ahead and put this set up in synthetic division form. So you have 2 is a 0. And it's going to bypass the line division setup. So you got 2 is a 0. And the remainder should be 0 if 2 is a 0. Okay, now we have with the dividend. So you have x squared minus 6x plus 4. So there's no missing degree term. So you got 2 for 2x squared, negative 6 for the first order x term. And then we have the constant value 4. And so looking at what we have here, okay, so you have 2 at the front, and this is going to be brought down, okay, and then we have 2 times 2 is 4. Then we have negative 6 plus 4 is going to be at negative 2. And then we have 2 times negative 2 is negative 4. And 4 plus negative 4 is 0. So again, we want the remainder to be 0, which it is. Okay, now in terms of the factors, now 2 is a 0. And if 2 is a 0, think of it like working backwards when we looked at like setting up factor and expanded forms of polynomial expressions. So for the given 0, we have think of like x equal to 2. And if I set the equation to 0, I would have x minus 2 is equal to 0. So from the 0 value of 2, then we'll have the divisor. It's going to be x minus 2. And again, the 2 in the dividend was in reference to 2x squared, but for the 2 at the front and reference to the quotient, this will be in reference to 2x. So the quotient here, okay, so that's going to be 2x minus 2. And for the factoring, okay, so you have f of x again. We have equal to 2x squared minus 6x plus 4. Again, so you have from the quotient, I'll use a little bit of color coding here. Quotient we have at 2x minus 2. We have times the divisor, which we have at x minus 2. And if I factor it completely, so you have 2x minus 2, so I got to have a factor of 2, and have times the quantity of x minus 1. Then I have times the quantity of x minus 2. So that will be the complete factorization of what I have for this polynomial function. And let's say that if I have I can show you this too, especially if you've got I think about like some of the items in ALEKS that can get a bit particular, especially if you have a repeating factor. Say if you have factoring f of x is equal to 4x cubed minus 20x squared, we have plus 33x minus 18. And say given also that 2 is a 0. Okay. All right, so if I set things up, okay, in line with synthetic division, okay, so I have 2 as a 0. It's going to mention, okay, so just checking and applying the synthetic division setup. So I got 4x cubed minus 20x squared, 33 times x, and I have a constant with negative 18. So everything from the third order down to the constant, okay, is going to be consisting of some term. Okay, so I got 4 for 4x cubed, negative 20 for the x squared, 33 for the x, and minus 18 for the constant. So no 0 was needed for placeholder purposes. So we have here, so if I bring down 4, 2 times 4 is 8. Negative 20 plus 8 is negative 12. 2 times negative 12 is negative 24. 33 plus negative 24 is 9, and 2 times 9 is 18, and negative 18 plus 18 is 0. So again, if the assigned value is a 0, then the remainder should be 0. And we have just a little bit of history to repeat. Okay, so you had the divisor is at x minus 2. In the case of the quotient, now the 4 above was in reference to x cubed. Now that it is brought down, you'll have 4x squared minus 12x plus 9. And so just looking at the factorization, okay, so you have with the quotients, you have 4x squared minus 12x plus 9. And you have times the divisor again, which I have x minus 2. Okay, now I'm going to factor this part out. Okay. Think of it like factoring by grouping. Okay, so you got like 4 times 9 is 36. And factors of 36 will add up to negative 12, be like negative 6 and negative 6. So you'd be looking at like 4x squared minus 6x, and then you have minus 6x plus 9. And if I were to factor by grouping, what this expression would condense to, okay, we have identical binomial expressions for which we will have 2x minus 3 times itself. Then we have times the quantity of x minus 2. And again, just condensing, since I have a repeating 2x minus 3 and it appears twice, so I have for the complete factorization of this cubic polynomial, this is going to be the square of the quantity of 2x minus 3 times the quantity of x minus 2. Okay, and just a case here, so it just has it's a bit of a quick exercise, and let's see what we get. And we'll just need the quotients and divisor on this one. Okay, let's say that we have factoring. So we have f of x is equal to 3x cubed minus 41x minus 28. Notice we don't have an x squared term, so there had to be some kind of modification on this one. Okay, so we have factoring f of x equals 3x cubed minus 41x minus 28, and we'll say we have given that 4 is a 0. Okay. Okay, so we have for this polynomial, okay, so again we have 4 is a 0. If we go ahead and set things up in terms of using synthetic division, so 4 is a 0, and now setting up what we have now, okay, so we got f of x, and we have is equal to 3x cubed. Notice we do not have an x squared term present, so I'm going to use 0 for placeholder purposes. So this is for x cubed, this is for x squared, and for x to the first I have the coefficient negative 41, and again closing out with the constant, I have negative 28. So looking at what we have now, okay, so the leading coefficient from the dividend will be the leading coefficient in the quotient. So 3 is brought down. Then we have 4 times 3 is 12. 12 is brought over into the next column. So we have 0 plus 12 is 12. Next, 4 times 12 is 48. So this will be brought over to the next column underneath negative 41. And negative 41 plus 48 will make 7. And then we have 4 times 7 is 28, and bringing this over, and we now have negative 28 plus 28 is 0. Again, so we want the remainder to be at 0. And for what we have in terms of the divisor and the quotient, so with 4 as a 0, like x is equal to 4, okay, we're going to have x minus 4 is going to be the divisor. And for what we have for the quotient, okay, the 3, 12, and 7 will reference this time 3x squared plus 12x plus 7. So we have, in terms of factoring, we have that f of x is equal to 3x cubed minus 41x minus 28. Again, we have equal to the quotient. So you have 3x squared plus 12x plus 7. And you have times the divisor, which will be x minus 4. And again, this will be the complete factorization in integer terms, because if you tried factoring by grouping with a trinomial, you would have like 3 times 7 is 21, and there are no integer coefficients that will add up to 12 and simultaneously be factors of 21. So you think of like 7 and 3, they will add up to 10. And 21 and 1, well, those will add up to 22. So this will be the simplest form of what we have in the complete factorization in accordance with integer coefficients. So that will be the result here. All right. Now, working with, in another sense, the continuation of polynomial division, but kind of going back to the topic of domain. And we have in the next section, and this is going to be what we have for domain and vertical asymptotes. Of rational functions. Okay. And we'll have for a rational function, r of x, okay, so for a given rational function, r of x. Okay, now the domain, you have a lot of repetition with the terminology from before. Now the domain, again, we have the set of all values of x such that the rational function such that r of x is defined in the real number system. Now, for what we have regarding vertical asymptotes, okay, and in case of what we have with a vertical asymptote, vertical asymptote is going to be a vertical boundary that's going to separate r of x into separate sections. And it's going to be formed by exclusions from the domain. Whose factors remain. And just stressing, and this is going to be after R of x is reduced to lowest terms. And just a couple of cases here. Okay, say if we have if you were to determine the domain and vertical asymptotes, if any. Okay, and there is such a thing as something having asymptotes but not necessarily vertical asymptotes. Okay, but now let's say we have first of all, we'll say we have for the first function, and we'll give one that is already in simplest form. So we just say that we have R of x is equal to the ratio where we have x plus 1 divided by x plus 4. So that ratio is already in simplest form. Now, in terms of the restrictions, now again, for a rational function with a fraction, the denominator cannot be equal to 0. So x plus 4 cannot be 0. So x cannot be equal to negative 4. So x can be anything but negative 4. Like you can have x at negative 1. You can have a 0 numerator as long as you do not have a 0 denominator. So we have for the domain, again, in the interval notation, okay, you have those values of x that will be less than negative 4. So you have parentheses around negative infinity and 4. And then for the other half, you'll have those values of x that will be greater than negative 4. So you have after the union symbol, you have parentheses grouped around negative 4 and infinity. All right. Now, for R of x, okay, R of x is already in simplest terms. That is completely simplified form. So this means that, okay, for the exclusion from the domain, okay, x plus 4 remains. Okay, so this means that for the vertical asymptote, for the vertical asymptote. Now we had the exclusion of -4. Okay, but since x plus 4 sticks around because r of x is already in simplest form, so x plus 4 is not going to cancel. We'll have a vertical asymptote, which is going to be at x is equal to -4. And just looking at what we have, say just on a visual basis. Okay, so you see what I have with the XY coordinate system. Again, I'm going to do kind of a sketch, but just kind of point out some of the main elements here. So we have so you have a vertical asymptote at x equal to -4. Okay, this is going to be a vertical boundary, okay, that is going to separate the graph of r of x. Okay, so you got your vertical asymptote. I'm just going to say V8 for vertical asymptote. Okay, so we have x equal to -4. Now for what we have in the case of the graph of r of x, now this vertical asymptote is going to split the graph. And in terms of how this is going to sort of look, okay, I'm just sketching. Yeah, I'm just sketching, not drawing to scale. Okay, but you have these two sections here. And this will be with regard to r of x is equal to x plus 1 all over x plus 4. In the case of, let's say, where the stressing of reducing to lowest terms is going to be required. And so we have r of x, okay, so we have equal to x squared minus 1. And we have all over x squared plus 3x plus 2. Okay, now this particular rational function is not yet in simplest form. But again, before the simplifying, you're going to go ahead and take the restricted values. So again, x squared plus 3x plus 2, because it is in the denominator position, cannot be equal to 0. And the factors of the trinomial we have x plus 2 and x plus 1. Again, we have with the factors, okay, we have x plus 2 cannot be 0. And x plus 1 cannot be 0, so we have two values in x that will be left out. So you have x cannot be -2, and we have the x cannot be -1. So you have for the domains, you have both -2 and -1 are left out. So we have those values of x less than -2. Then we have those values of x greater than -2 and less than -1. And then you have, for the rest of the domain, you'll have those values of x that will be greater than -1. Okay. So again, you find out what will be excluded, okay, before you reduce. Now, for r of x equal to x squared minus 1 all over x squared plus 3x plus 2. Okay, so I've already got the restricted values. Now if I look at factoring, so we have with x squared minus 1, so you have the quantity of x plus 1 times that of x minus 1. And for x squared plus 3x plus 2, if I factor, say the quantity of x plus 2 times that of x plus 1. Okay, and if you notice, we have a common factor with x plus 1 in both the numerator and denominator. So I'm just going to go ahead and kind of write this again. So we have x plus 1 is going to cancel out. And for the completely reduced form, okay, so we're going to have x minus 1 all over x plus 2. Okay, and again, we had the exclusions from the domain to come from the factors of the denominator, where we had x plus 2 and x plus 1. Now x plus 1 canceled out. Now x plus 2 remains. In other words, it is not canceled out. So we have for this, x plus 2 remains. So that means that x, our vertical asymptote, there could have been two vertical asymptotes, but there was one instead. And so you had the vertical asymptote will be the 0 of the denominator. So the vertical asymptote, we're going to have an x equal to negative 2. Now for x plus 1 cancels. And with canceling, instead of becoming a vertical asymptote, the 0 from this, okay, x equals negative 1, instead of a vertical asymptote, that is going to be a hole in the graph. And just for the kind of the appearance of this one, especially in itemizing, okay, just what we have regarding the domain and the general behavior of the graph of this rational function. Again, so you have the locations on the x-axis of interest. You have negative 2 and negative 1. Again, you have a vertical asymptote with x equal to negative 2. And just for the graph itself, okay, so we got, again, I'm just kind of doing a rough sketch here, but we're going to have, again, just like earlier, we have the region to be split up. And just like for the other portion here, so you have, as the graph is to the right of the portion that is to the right of the vertical asymptote, as it is increasing. Okay, once we get to x equals negative 1, there's going to be a hole in the graph. And for the rest of the graph of this function, okay, so both of these portions will be in reference to r of x is equal to x squared minus 1 all over x squared plus 3x plus 2. Okay. Again, just to mention, okay, so again, so we have a whole at x is equal to -1. Okay, so any zeros whose factor will completely cancel out from the denominator. Okay, that's going to become a whole. But if we have any remaining factors in completely reduced form, like in the case of x plus 2 remaining, that means that the 0 from this is going to become the vertical asymptote. And let me mention this. Now the vertical asymptote, again, divides the graph up into separate sections. And one might be wondering, okay, in the case of graphing, and let me mention this, okay, so the graph of r of x never touches a vertical asymptote. Okay, so vertical asymptotes will be off limits, and we'll be looking into other types of asymptotes that will not be quite so off limits, but for vertical asymptotes, yeah, the graph of a rational function will never touch it. All right, can't touch this.